So, what I want to look at now is magnetic fields and magnetic behaviour. Right, okay, so in the last lesson we established that a magnet will have two poles, a north-seeking pole and a south-seeking pole. If a magnetic material has been turned into a magnet, in other words, if we've got iron, cobalt, nickel or steel, and they have been turned into a magnet, then this is what the magnetic field will look like. So this is the area of non-contact force that is being exerted by the magnet. It is strongest at the poles, so this is where the magnetic field is strongest, and it is weakest further away. So if I was to place a magnetic material far away from this, it will experience only a limited amount of attraction. Okay, so a magnetic field can attract or repel other magnets, so things that have been magnetised. It's only attractive for magnetic materials that have not been magnetised. In other words, if you've got iron, cobalt, nickel or steel, but it's not behaving as a magnet, it's not been magnetised, then it will be attractive in the magnetic field. Let's have a look at the magnetic field shape. So, you will notice this pattern. It's the same for a coil of wire, known as a solenoid as well, that's got electricity passing through it. And what you'll notice is the arrows point away from the north. That's right. Magnetic fields travel in a direction from north to south. So if we imagine a tiny test magnet, which mass is so small that it's not going to have any effect on the magnetic field or gravitational fields, then it behaves as a mini north. Okay, so your test magnet, okay, is repelled from the north pole and attracted from the south. You could be expected to label the direction of these lines. Please pay attention to this, it will be worth a mark. Compasses are devices that help us to navigate. A compass, the arrow will point towards the north. Okay, so you've got your geographical north pole at the top, and you've got your geographical south pole at the bottom. Controversy is, we know that if the Earth does have a magnetic field, but it does have a magnetic field, then the north pole is there, the south pole is there, so north and south geographically are the wrong way around, because north should repel north, and therefore it should be pointing to the south. But hey, that would cost a lot of money and annoy quite a lot of people. Now, you can use compass behaviour to plot this. Okay, so what you would do is you take a tiny compass and you place it at regular intervals around the magnet. And what you would do is you lift up your compass and draw a pencil marking to say which direction the compass was working in. And what you would find is the compass arrows follow exactly the same behaviour as this. So for 3 marks, you could be asked how to use a compass to draw a magnetic field pattern. Place it at regular intervals, draw the arrow on your graph paper, and then finally you can join the lines up. Okay? Because compass behaviour is determined by the magnetic field here, we must conclude that the Earth must have its own magnetic field. Otherwise, why would the compass behave in the way it does? And we actually know that in the iron core, we've got a convection current going round and round, and that convection current is what's causing the Earth's magnetic field. Don't get me started, however, on the idea that it's going to flip at some point. It will. We don't know when. Thank you.